So we've just watched a video of a ping pong ball recoiling at high speed off of a basketball. So let's look at the physics of that situation and see if we can understand why it was such a dramatic demonstration. So first I have a ping pong ball falling with some speed, and it's going to hit a basketball that's traveling in the opposite direction at some speed. And now since these things have dropped from the same height, they fall in the same distance, and so effectively, if I draw the ping pong ball speed, let's call it u, and the basketball's recoil speed off the ground, we'll call that u as well, their speeds are effectively the same. And so we're going to write down the momenta for this situation. Let's actually pick a coordinate system. So let's see. Let's make the positive direction up. That looks like a reasonable thing to do. So clearly these are relatively bouncy balls. So this is the sort of epitome of the elastic collision here. And so we know that we can look at the relationship between the two velocities using our addition of velocities equation. So we can write that the initial speed, let's use a little v for the ping pong ball, the initial speed of the ping pong ball plus the final speed of the ping pong ball is going to be equal to the initial speed of the basketball, and we'll use a capital V for that, plus the final speed of the basketball. Now if we look at how we've set this up, the initial speed of the ping pong ball is downward, and we defined the positive direction to be up. So this is minus u, and we don't know what v final is yet. And that's going to be equal to the initial speed of the basketball, which is going to be plus u. And now we're going to make an approximation. We're going to say that the speed, the final speed of the basketball is pretty small. The change in speed of the basketball, excuse me, is pretty small. And so its speed doesn't really change at all, so it's approximately equal to u. So v final is approximately equal to u, which is approximately equal to v initial for the basketball. So if we make that approximation, we can see that v final of the ping pong ball is going to be equal to, if I move this minus u over to the other side, is approximately equal to 3 times its original speed. And so when we look at the demo, the ping pong ball goes flying off at high speed, and so it's approximately 3 times its original speed. Now there's another way to consider this. If we move to, just since we were talking about reference frames, if we move to the basketball frame, to move to the frame where the basketball is at rest. So that's the basketball frame. So we're moving along with the basketball. If we do that, then let's look and see what we see. In that frame, the basketball is at rest. And so it, since the ping pong ball is coming at it with velocity u in the lab frame, that means that the original velocity of the ping pong ball in the basketball frame is actually equal to minus 2u. And if we make the assumption that the velocity of the basketball doesn't change, that means that the ping pong ball comes in, bounces off it, and goes back out with the same speed. So v final in this frame, let's call this the primed frame, is equal to plus 2u. So the basketball looks like a wall. It's an elastic collision. And so this is the elastic collision condition of the ping pong ball. It's original, it just reverses its direction and goes back out. So if we look at that case and then we go back to the lab frame, I have to add back the velocity of the center of mass to these things. And the velocity of the center of mass is effectively the same as the velocity of the basketball. So that also tells us that v final of the ping pong ball in the lab frame is equal to 3u. So we get the same answer, but it's a different way of looking at this system. So that's our elastic collision example using a effectively massless object and a very massive object. And you get what effectively is an addition of the massive object's speed to the bounce of the other one. And so it goes flying away.